So our next speaker is Amara Katabarwa from Zapata Computing. So Mara, welcome.
Thank you very much. Let me share my screen.
Sure. Okay, we can see your screen.
Is this okay?
Okay, the floor is yours.
Thank you very much. So sorry if I sound a bit sick. Hopefully everything goes correctly. So my name is Amara Katabarwa. I head the hardware team at Zapata Computing, and thank you for inviting me to this conference. So actually, I'm going to talk about an algorithm called robust amplitude estimation. And I'd like to first acknowledge a few collaborators that I worked on this project with. Alex Kunitsa is a scientist in our professional services team. Peter Johnson, a founder, and also the lead research, the lead for the research team, and Borja on your right, who has now moved to IBM, but was at Zapata while we conceived this project. So I would like to sort of begin this talk by trying to sort of motivate this problem. And what I'd like to sort of divide is the community in sort of the hardware vendors and the sort of quantum computing software companies, right? So it's very easy to see why, you know, Google, Honeywell, Rigetti, and so on, these hardware providers are in this game, right? Because we all believe fault-tolerant quantum computing is possible, and you know, a journey of 1,000 miles begins with a step. And so at some point, you have to produce a 5-qubit chip, you have to produce a 10-qubit chip. And so it's understandable that there'll be an era of computing where, you know, you're not doing full quantum computing, but you're coming close to it. So it's easy to see why hardware providers are in the game. But why startup companies like Zapata in the game, right? I'm not going to mention any other software companies, but you can substitute in any company you have in mind. But you know, why are we in the game? After all, we're not yet doing fault-tolerant quantum computing. And if I give you a 100-qubit machine, it's not completely obvious that you know what to do with it, right? Because you can't do error correction. And I would say the reason we're in the game is really these hybrid quantum classical algorithms. What was discovered is that there can be a sort of interplay between quantum processing units and classical processing units, and we can sort of divide the efforts between the quantum processors and the classical processors, overload some of the computation to the classical processors, and hopefully as quantum processors get better, we can put more workload on the quantum processing unit. So that got a few people who are very sort of visionary about these quantum classical algorithms to begin thinking about industry level applications, starting and helping to found companies. So really, it's, you know, there are a number of examples. I'll just state a few. We have variation quantum eigensolver, finding ground states for Hamiltonians. We have VQS, variational quantum simulation, which helps with the sort of dynamics. We have QITE, which helps with imaginary time evolution. QVector is one, which is a proprietary algorithm from Zapata, which helps with finding quantum error correcting codes that are tailored to the device. We have QCVM, which is used in generative modeling, quantum circuit board machine, and so on. So I mean, there are many more variational quantum algorithms, and the speaker we had before sort of gave his own list. But I would like to concentrate on VQE. Okay, so why VQE? So the idea is that we want to use a variational principle to find the ground state of some Hamiltonian. And so we have an ansatz, a wave function, which is parameterized by some knobs, some angles. These knobs and angles are input by some rotational gates, either single qubits and or controlled operations, entangling operations. And we're going to use them and hope that by using the quantum processor, we can sort of solve this representability problem of the wave function. And the quantum processor in this case is meant to act like a scalable way to sort of hold the wave function of the quantum state. Of course, there are problems related to this algorithm, which are well known to some of you and probably all of you, which is that you need to find these parameters, the optimal parameters, to minimize the energy, and so some effort needs to be done in doing that. So quite a bit of effort has been invested in making VQE better, in hopes for sort of using this as a flagship algorithm to start companies and hopefully find some quantum advantage. So the number of things you can do, there people have studied Hamilton transformations, Jordan Wigner, Brad Vikitayev, disparity encoding, sort of to reduce the overhead on quantum resources. There's a lot of work that's done on ansatz design, finding good initial parameters. Again, the previous speaker has spoken about the problems that come with like barren plateaus, but also designing the ansatz itself, even before you begin thinking about initial parameters. And of course, there are things like the Hamiltonians are usually can be broken up into summation of Pauli operators, and then you probably could measure certain groups of Pauli terms together, like they're probably so-called commeasurable. How do you optimally do that? A bunch of papers have gone into figuring things out like that. As you're trying to, as you have a budget of samples or shots, you can think about shot assignment strategies. Again, just to the Patrick Hole's group in Los Alamos has been really good with papers like this. Of course, I have to think about optimizers. Here, I'm thinking of Google, as Google Quantum AI has also done brilliant work in this effort, and of course, there are other people who are interested who have spent some time trying to figure out how best to optimize this VQE. And then analytical gradients. If you have a gradient-based optimizer, how do we best calculate the gradients? And also, I'm thinking of people like Maya Schuld, but also other people. Atur in University of Toronto has done brilliant work on this. And of course, you have to think about error mitigation, since we don't have fault-tolerant quantum computing. Here, I'm thinking about things like noise extrapolation. I'm thinking about like virtual state distillation. I'm thinking about probabilistic error cancellation. So a lot of effort has been put into making VQE better. Okay. But the question that I'd like to pose, and this really set the stage for my talk, is that can we get quantum advantage with VQE? Okay. So a lot of effort has been spent in trying to make VQE really good. Okay. So this is a question that Zapata a couple of years ago, actually more than a couple of years ago, something like 3 years ago, decided to really investigate with a customer. And the output of that is this paper, okay? And what we conclude is that, no, you can't get quantum advantage with VQE. Okay, so for any industrial level applications, we don't expect VQE to be the source for quantum advantage. So why? There's an elephant in the room that very few people talk about, but I remember a couple of years ago at conferences, people asking me about VQE, and it seems there's been this quiet worry that people have had every now and then. And the worry people have had is this thing here. Okay, K here is a constant. M here is a number of shots. Epsilon here is the precision required. And what has worried about a bunch of people and what was worried Zapata is that 2. 1 over epsilon squared. This is the elephant in the room. It turns out that this is a really, really, really slow scaling. It's really a problem. And this table you can find in this paper here. But I think for me, it summarizes the problem with VQE. So again, we're investigating VQE for industrial level applications. So we're not going to play games with hydrogen or beryllium, whatever. We're trying to figure out if we throw all the tricks that are in the literature to VQE and try to give it the best possible chance to do what it can do, what should we expect for VQE for industry level applications? Here, the group that did this work at Zapata was interested in chemical reaction, things like that. So the lowest time you can see here is 1.9 days, and this I emphasize is for one energy evaluation. Okay, so this is putting in parameters in your wave function, doing everything you can do, and doing one energy evaluation. The lowest number we have here is 1.9 days. The highest number is 71 days. Now, in VQE optimization, you're actually doing hundreds and maybe even thousands of energy optimizations. So that means that for any industry level applications, chances are, barring some amazing progress in optimizing or something, the optimizing VQE and getting ground state energies is going to take on the order of years. So we don't think VQE is a thing to do. So here comes the purpose of my talk, introducing robust amplitude estimation. So again, the research team and the research team got into this problem. Once we discovered that VQE was not going to be the pathway forward, a bunch of people, Guoming Wang, Dax was a postdoc at Zapata, Peter, who was the lead, Yu Dongtao, who was the CTO, went and began to think about this problem. The output of this was what we now call robust amplitude estimation. And what this does is that it has a better scaling than VQE. It gets rid of this 1/epsilon² scaling. And what I'm going to talk about is the derivative of those two papers. So the purpose of the third paper here is that once I read these papers, there were a number of assumptions that bothered me, and I wanted really to see how this would really work. I'm trying to make this, I'm trying to see whether this could work on near-term devices. After all, I head the hardware team, and I'm interested in trying to make things work on quantum hardware. So we made a few adjustments to the original papers, got it even more near-term friendly than it was before. And the output of that is this paper that I'd like to say something about. So anyway, so just at the top level, what happens is that the new kind of scaling we have is that it interpolates, really, this algorithm interpolates between the standard sampling, 1/epsilon², to the Heisenberg, I think there might be an error. Anyway, to the Heisenberg limit, and there's some interpolating function. So the ingredient of this algorithm are what we called enhanced sampling circuits. So what are they? So on the top left, we're going to use standard sampling. Standard sampling is what we know about from VQE. So we have an initial state. We prepare the ansatz in red, and then we measure the expectation value of some Pauli operator. So we're going to modify that by this so-called, what we call enhanced sampling circuits. And a layer of this enhanced sampling circuit is going to be the Pauli operator, inverse ansatz, a reflection operator from, think about Grover's algorithm, and the ansatz layer. So this will be a layer. And we call this the Grover iterate. So what's happening here? In order to understand what's happening here is that the trick here is to really pay attention to what's called the likelihood function. The likelihood function for VQE is a linear function. And for at least layer equals to 1, the likelihood function is really a Chebyshev polynomial plus some constant. And the point of it is that if you look at the slope of the graph in your top right, the slope squared is proportional to the Fisher formation. Okay. So we know from the Kramer-Rao bound that higher Fisher formation means that you can improve the sampling efficiency of your estimation method. And what these enhanced sampling circuits are doing for us is that they have a steeper slope. They're much more sensitive to the estimation of Pauli operator than VQE. And so they're giving us steeper slopes at at some value of the Pauli operator. Of course, there are places where the slope is getting close to zero, and those are called dead spots. We call them dead spots. And the much more general algorithm that was worked at is called engineered likelihood functions, and it helps get rid of these dead spots in the facial formation. But for general L, as you have more of these Grover iterates, you get general Simon Chebyshev polynomial, and it has that form. Okay, so what about noise? So what the scaling that I showed you earlier, that lambda was related to some deep horizon constant. So the simple noise model, which we can think about as the Bohr's atom of noise models in quantum computing. Of course, things are much more complicated on the real devices. We're going to assume that the unitary is applied with probability p, or you get a completely mixed state with 1 minus p. Here, the unitary is a layer, a layer of your circuit. And you can reparameterize this noise model and introduce exponential factors, and then parameterize in terms of this so-called lambda, and all the complexities of the noise that appear in a circuit, in a layer of a circuit in the Grover iterate, can be sort of rolled up and balled up in this constant called lambda. And so the modification of the likelihood function in the presence of noise is going to be given by an exponential damping of the Chebyshev polynomial. And what you can see is that it's decreasing, helping decrease sort of narrow, or I guess what can I say? It's meant to reduce the steepness of this slope. So that's the effect of noise. Okay, so what I was interested in is that how good does this work on actual quantum devices, and what can we learn? How can we make this work? So let me see. Yes. So we're going to start with a 2-qubit experiment, and we're going to use this ansatz. This is usually used to find the ground state of a molecular hydrogen atom, and we have 2 C0 gates in it. So what we'll do is that we will have this ansatz. We'll perform enhanced sampling. We'll add on these enhanced sampling circuits, and we'll run them. And I don't know how much time I have, but let me just roughly quickly say what's happening here. The details don't matter, but what's happening here is the input here, this curly M, you can think of as the parity bits. Once you measure your quantum computer, you have these bit strings coming out, and you can sort of calculate these parities based on where your Pauli operator acts. And you can do this for a number of layers. So here, L max is going to be, I don't know, you can run a circuit, let's say, with 2 Grover iterates, 3 Grover iterates, 4 Grover iterates until some max layer. And so when you're getting these measurements, you have bit strings from circuits with different number of Grover iterates. And there's a maximum likelihood estimation algorithm to get out the estimate of your Pauli explicit value that you can then report. So what are the results? The results are, let's concentrate, I guess, on the left. So we tried with Bellum and Manila, and as you can see, as you increase the number of layers, the bias improves. Of course, there's a point of diminishing returns where the noise begins to impact things more. But what's surprising is that it's not completely obvious that just adding the depth of the circuit makes things worse. So for example, if you look at Manila and the X0, X1 operator, the bias improves even with larger deeper circuits. And we tried up to 10 Grover iterates, which is roughly about 50 C0 gates. So on the right, we're graphing the precision versus the bias. And for Bellum, you can see that we really got the optimal number of Grover iterates to be around the 3rd Grover iterate. So both bias and precision are improving. In other words, the RMSE is improving until about the third Grover iterate. From Manila, things are a bit more amazing until about layer 7 or 8. And then after that, things get a little bit worse. So the outcome of this is that we can do better than VQE. So in the paper, we go into some trouble to make sure that we're going to compare VQE and Ray in a fair way, because remember, for these Grover iterates, in principle, to improve precision, you have to run deeper circuits. So although you're getting improvement in precision, you're taking more time. And so we set things up in such a way that we could more fairly compare VQE and Ray. So that meant usually that it meant that we had to give more samples to VQE and less samples to Ray, robust amplitude estimation, in such a way that things are approximately on equal, the two arguments are approximately on equal grounds. And in that case, on real devices, we found that we'll get about a factor of 2 improvement in precision. And again, what was surprising to us is that we also get an improvement in bias by up to a factor of 10. So we can do better than VQE, and as devices get better, we believe that this robust amplitude estimation is the way to estimate expectation values of Pauli operators. I can go, if I have time, I can go rough into what's happening with the bias, because it's kind of counterintuitive, as running deeper circuits can help you reduce the bias, despite of the fact that things should be a bit more noisy. So it's something we're trying to investigate, but I think I have a few ideas of why that could be true. But I'm coming to my sort of the main takeaway. One of the main takeaways of this work is that we should really think of quantum coherence as a precious resource, and we should be more bold in terms of how we push the devices. So what this graph is supposed to show you is graphing the phase information per unit time. Unit time here just means 2L plus 1, where L is the number of layers. And remember, a layer involves having 2 applications of an ansatz and this oracle. And this is graph got from the lambda that we got from Manila. So this is a graph that graphing the facial information from actual device. And what you see is that the facial information gets maximized at I think about layer 7. So if you're willing to push the device further, we can really get more out of quantum coherence than you would naively think. And the trick I think for me is from now onwards is how do we push the devices more than we're pushing them, and how do we do that in a very clever way. And I can talk more about this if there's time for questions coming to the end, about how that's factorially done in the literature without people really knowing what they're doing. So what we should really think in terms of devices and using them is that there are 2 competing forces. There's an increase of facial information got by using deeper circuits, and there is a decrease of facial information due to noise. And the optimal depth you should use is really got by trying to balance these 2 countervailing dynamics. And optimal depth could be, in fact, deeper than you thought. And so we believe that robust amplitude estimation is a key step to using quantum coherence as a precious resource, and trying to use it, and hopefully we believe it will use it more efficiently as devices get better, and sort of eke out the most of quantum coherence as we sort of seek quantum advantage. So thank you for listening. I think I've left some time for questions.
Yes, thank you very much, Amara, for your talk. So let me check if we have any question from the chat. Okay, no. So in the meanwhile, let me ask you a question. Actually, it's more like a curiosity rather than a question. So you told us that it takes 1.9 days, if I remember correctly, for estimate a single level energy level by using VQE. What about robust amplitude estimation? Is it possible to estimate, the time that it requires to
so that's work coming out soon. That's work coming. So what I showed was, that's the first phase of a whole bunch of work that's been done.
Okay.
And so the first step is to show that VQ is not the way. The second step is to show that we have a different algorithm, and then the third step is to show that there are improvements in the algorithm. So that's paperwork coming out soon. And from my point of view, because since I head the hardware team, is to begin to run these things and try to figure out how best to use these algorithms in the here and now, and how to use them in the most efficient way, how to sort of push the devices. So that's where coming out soon. So I'm not sure how much I could talk about it, but
okay. Thank you. Thank you very much. Thank you for clarifying that. Okay. Thank you very much. So
there's hope.
If there is no question left, so I thank you, Amara, for your talk. It was very interesting. And so now we have a 15 minutes break. So we resume at 5 p.m. So, well, okay, so let's resume in 15 minutes. Thank you.